All right, well, welcome back to Real Analysis. We're going to continue our work in Chapter 8 in Section 8.3, looking at the second form of what's called the Fundamental Theorem of Calculus. Okay, so in our book, this is Theorem 8.9, so I've got it numbered like that. And let's just walk through the statement of the theorem and then through the proof. So once again, it's about a function on an interval, so sort of the usual preamble. We'll take two real numbers, a and b, assuming that a is less than b. And then the hypothesis on this function, capital F, is that it's differentiable on the interval from a to b. Okay, the closed interval from a to b, one-sided derivatives at the endpoints. And then we're going to be assuming, in addition to that, that its derivative is continuous. So it's a rather strong assumption on the function f, because we know that the derivative of a differentiable function need not be continuous in general. So we are adding that hypothesis here. So we've got a so-called continuously differentiable function, capital F, on this closed interval. And then what does the fundamental theorem say? Well, this is the way you computed most definite integrals in calculus. It says that the definite integral of the function f prime of x, the rate of change, if you like, of capital F over a to b, is the so-called net change in f. You take the value of f at b and subtract the value of f at a. In calculus classes, typically you're given sort of the f prime function first, and so you call f an antiderivative for it. And that's what you were taught in calculus. In order to compute a definite integral for a function, you find an antiderivative for the function you're integrating, and you evaluate that antiderivative at the two endpoints, subtracting in that order. All right? So we're just going to give a proof of that based on our kind of development following Cauchy of this notion of the definite integral. Okay, so using the theorem to state the hypothesis, let's just start working through here. So first of all, we're assuming that f prime is continuous, so it's part of the hypothesis. So that Cauchy's theorem, theorem 8.1, says that that function has a definite integral, f prime, I mean. And more precisely by that, I mean if we are given any epsilon, there's some delta, so that if you take any tagged partition p dot, of the interval AB, so you have these n subintervals and you chose the tag C sub k, any tagged partition whose norm is less than delta, well then the Riemann sum of f prime, I'm applying theorem 8.1 to f prime, the Riemann sum of f prime differs from the value of the definite integral of f prime by less than epsilon in absolute value. So I'm using that Riemann sum notation here, S f prime of p dot, but here I'll remind you what I mean by it. S of f prime of p dot is just the sum, plug the tags, the C sub k's, into your f prime, multiply them by the corresponding subinterval widths, and sum those things. So that's our notation for Riemann sum. Okay, so because f prime is continuous, Cauchy's theorem says that given an epsilon, you can always find a delta, that no matter how you pick this tagged partition, as long as its norm is less than delta, this Riemann sum will differ from the value of that integral by less than epsilon. Okay, so then let's take a partition, P. We won't tag it yet, but just take any partition P of AB whose norm is less than that delta. So we haven't chosen the tags yet, but given an epsilon, there exists a delta. So pick a partition whose norm is less than delta, okay? And then let's look at the function f on any one of the subintervals from xk minus 1 to xk for that partition. F is continuous on that interval. It's differentiable on the open interval because f prime exists over the entire interval from AB. So f would satisfy the hypothesis of the mean value theorem on that subinterval for every single value of k. So that's how I'm going to pick our tags. Okay, for each k between 1 and n, there has to be some number, I'm going to call it c sub k, our tag notation, so that the change in the output of f, I'm applying the mean value theorem to f here, the change in the output of f is the derivative at ck times the width of the corresponding interval. So I'm applying the mean value theorem n times. I'm applying it for each one of our subintervals. Okay, so now from this partition P that we started with, whose norm was less than delta, well, we've tagged it. So that's how I'm going to select my tags. I'm going to select them to be the numbers that satisfy this mean value theorem condition. So now I have a tagged partition less than delta. Well, that means that its Riemann sum differs from the definite integral by less than epsilon in absolute value. But the Riemann sum for this tagged partition will be particularly pleasant. If we look at what the definition of that Riemann sum is, well, we just wrote above that you plug in the tags into f prime and multiply it by the corresponding widths. But we just said, maybe I can back up, I can show you here again, each one of these things, f prime of ck times this subinterval, I can swap it for the difference of fk, capital F of xk and capital F of xk minus 1. Okay, so if I kind of use some different colors to indicate that, I'm swapping out the left-hand side for that difference, summing from k to 1 to n. But if we write out that sum, I tried to make it a little bit easier to see what I'm doing. If I let k equal 1, I would get this term right here. I'll just sort of write it above. F of x1 minus f of x0, and then here's the k equals 2 term, and so on. This would be the k minus 1, or sorry, k equals n minus 1 term. And this is the k equals n term. And that's a so-called telescoping sum. Lots of the values in this sum show up with opposite signs. For example, this capital F of x1 has its opposite in that sum, so they eliminate each other. Capital F of x2, well, in the next term that I didn't write here, there would be a minus capital F of x2, and so on. This capital F of xn minus 1 shows up in the next term with the sign minus. This sign minus f of xk minus 2 would have canceled with the first term that's not written there to the left of it. So when you boil it all down, what survives? Well, you get the opposite of f of x0, that is the opposite of f of a, plus f of xn, that is f of b. Nobody cancels those terms. They only occur in the corresponding respective first and last terms in our sum. All right. So the Riemann sum, the sum telescopes, that Riemann sum over this tagged partition is just f of b minus f of a. But we already said that that Riemann sum, so f of b minus f of a, differs from the definite integral by less than epsilon in absolute value. Yeah, but those two numbers are not dependent on anything. F of b minus f of a is some number. This Riemann, this definite integral is some number. If the difference of two numbers is less than epsilon for any positive epsilon, then those two numbers have to be the same. Cool. So that's the proof of the second form of the fundamental theorem of calculus that we're going to use. It's based on Cauchy's theorem. Nice. Right. So that's kind of the crown jewel of almost any first semester course in real analysis, is to state and be able to rigorously prove that fact that you used commonplace in calculus courses, the fundamental theorem of calculus. Well, I mean, just listen to its name. It's the fundamental theorem of calculus. Okay, well, this video will be a little bit short, but I do want to throw in kind of one more result here. The so-called, that we just used the mean value theorem for functions to prove the second version of the fundamental theorem of calculus. There's another theorem that people usually call the mean value theorem for integrals. So I want to kind of state and give a quick proof of it. So same kind of preamble, we've got an interval, so a couple of real numbers, say a is less than b, and a continuous function, lowercase f, on that interval. Then the mean value theorem is saying that there's some interior point, some value of c in the open interval between a and b, where the definite integral, which exists by Cauchy's theorem because little f is continuous, is equal to the function value at that point times the width of the interval. I'll make a comment at the end of why this is called the mean value theorem for integrals. But we're going to derive it sort of using the first fundamental theorem of calculus. So if we apply the first fundamental theorem of calculus, it says that this function capital F on a to b that's given by the integral, capital F of x is the integral from a to x of little f. So again, remember, this is just kind of a dummy variable. It doesn't really even play any role. So I'm using the first fundamental theorem of calculus that function is differentiable on the interval from a to b, and its derivative is lowercase f at any x, right? So that's from the first form. So this capital F, therefore, is continuous because it's differentiable. And so I can apply the mean value theorem to it. I'm going to apply the mean value theorem to capital F. So the mean value theorem says that there's some interior point where capital F of A minus capital F of B, or sorry, I said it backwards, capital F of B minus capital F of A is the derivative, little f, right? Remember, this is just capital F prime of C times the width of the interval. But capital F of A, I'm going to kind of leave it to you to think through the details of why this is true. You can do it from the definition of definite integral. The integral from A to A of little f is 0. And of course, by definition, capital F of B is the integral from A to B. So if we take a look at what that equation, capital F of B minus capital F of A equals F of C times B minus A says, it just says that the integral from A to B of f is little f of c times b minus a, and that's the proof of the mean value theorem for integrals. I've got a little picture here to kind of illustrate, if you think about this definite integral, I'm kind of going to talk some calculus language now. We haven't really emphasized this application, but if your function f is non-negative on A to B, then this integral represents the area under the graph. So I'm just going to be a little bit brief here and write that like that. It represents the area under the graph. I've shaded it in blue there for kind of a fictitious f of x. You can see I've labeled that blue curve. It's some f of x. I've plotted it between a and b. So that integral represents the area. Well, the right-hand side, you can also think of the as an area. It's an area of a rectangle. I've shaded it in gray in the picture. So the mean value theorem for integrals is saying there's some function height. In my picture here, that function height is right there, f of c. There's some c between a and b, so that the area of that rectangle, f of c times the width of the interval, is equal to the area under the curve. Okay, so that's kind of a geometric interpretation of it. If I rearranged this equation, if I divide both sides by b minus a, which I can do, because we already said that b is not equal to a, then another way of algebraically stating what the mean value theorem for integrals says is that expression. Sometimes people call this quantity on the right the average value or mean value of the function f of x on the interval from a to b. Okay, so it's sort of the total, the integral divided by the width of the interval. In some sense, it's like the continuous analog of add all the function values together and divide by how many of them there are. But it's done over this continuous interval. So people call that the mean value of f, or the average value. So the mean value theorem for integrals is saying that the average value of your function is equal to the value of your function somewhere. Okay, so that's why it's called the mean value theorem. Okay, so we're going to keep this video short and end it there. Thanks for listening.